Hello and welcome. It's today the last session. And my name is Jarosław Rudzki. I am senior core engineer working with the CDPR. And today I'm going to talk to you about how small open doors can lead to better CPU utilization and bigger games. But first of all, I want to thank all the engineers that were involved in the work I'm going to present today. On the CDPR side, Andrzej Uszakov and Jarosław Bronisz, he was working with me to build some of the tech I'm going to present today. And on the Epic side, Dominic and Zach, they were very helpful with bringing some of the changes to the engine and working with us to make the Unreal better for all of us today. This talk is going to be about our experience with Unreal. We see some opportunities, but we also see shortcomings we have within the engine. And we're gonna focus exclusively on the CPU side because this is the specialty of mine, and we started with tackling this first. We want to present this thing right now because normally we talk about tech after we ship the games, but some of the things we built you can use already today, and maybe you're gonna have different ways you're gonna utilize that. We wanted to be sure that you don't have to wait for us to release the game to be able to understand where we were going for with those changes, but rather you can start today building your own things with the elements we brought to the engine. And I'm always looking for those patterns we have in how we change the engine, because I firmly believe that very often we do exactly the same things. And some of those things, maybe they should be part of the engine, so we don't have to repeat our work again and again, and we can improve for all people using the Unreal, and all people would have better experience. But disclaimer first, a lot of I'm going to say and show today, it's very experimental. And we don't really know if we're gonna ship with that, but I'm sure we're gonna change it over the time. And a lot of assets I'm gonna present for you today, they are part of the Old West learning material collection, and you can find those assets on the Epic Marketplace. So let's assume you want to build a game. You wanna build big open world game with lots of NPCs, with interactivity, large events happens in the scene. You wanna present a player with the fast traversal, because open world games are always about going through that world, exploring it, finding new cool places that you can visit. And let's imagine you have your game, you run the profiling on that game, and you have this frame, and this frame is 17.5 milliseconds, so seemingly you are kind of quite good to hope for 60 millisecond target budget and 60 FPS. If you look closely, you're gonna see that we have some NPCs moving around, we have skeletal meshes that update. But the issue happens when the player starts roaming around, when he starts moving. Seemingly, what you would see is that we start streaming. You have those two massive events that happen during that time. One is update level streaming. This is the place where we construct our actors, where we construct our game content. And at the beginning of the frame, we have processing of asynchronously loaded assets. We have async loading thread, but we still have to rely on a game thread to process post-load registration of some specific assets. But your game didn't change. The gameplay is exactly the same. But the frame, instead of being close to 16 milliseconds, is almost 30. And if you look what CPU is doing, the CPU utilization is quite low. We have some offloading to the worker threads for very specific systems like animations, but at the beginning of the frame and till the end, the utilization is quite low. There are cycles that we are not utilizing, and you are bottlenecked on the game thread. You would try to figure out how to optimize to it, but the only thing that you can really do is squeezing your game. What you would try to do is to put a bit smaller budget on the streaming, and maybe you're gonna merge some actors to have fewer those in the scene. But this is a compromise. This is something that scales back your game, or at least it makes development a bit more difficult. Because with high granularity, you can have faster iteration because you just change a portion of the level. With the assets, it's even a bit worse because the only thing that really helps you is to use fewer unique assets, and you have bigger repetition of that in your game. And if we have any lessons to be taken from Cyberpunk on CDPR side, is that the streaming is the most important thing for the open world game. You're gonna constantly stream in and stream assets. You're gonna constantly stream in and stream out actors, your content of the world. And if you really think about it, this gets a bit obvious because if something is behind you and you're moving away from it, you wanna stream it out as soon as you can to make a room for something that is in front of you. And if you are not doing that, that means that you don't achieve the full density of the world you potentially could have. And with word partition, you actually stream in and stream out the whole grids. And this granularity is not always, it's not always utilizing the potential of your world the best way. Like 95% of the time, those strict rules are okay, but you're gonna have very dense environment for specific locations. And for those, you have to have specialized rules for streaming. You have to have this great control for 5% of your game, for hero assets, for very unique location you're gonna build. And when we speak about streaming asset and streaming content, this is exactly what happens. And if we would do it properly, you will have to have it every single frame. So you don't have 16 millisecond budget for your game. You have maybe 13 millisecond if you're lucky. And in this talk, I'm gonna focus on update level streaming, on that part, because we have internally some answers to that problem. We're gonna get back to asset streaming for a little bit at the end, but focusing on that. When we analyze what we have in our open world games, most of that is static meshes. And they are not even static, they are immutable. There are walls of the building, there are rocks, there are mountains that we have. And to be honest, we don't need that much from those primitives. What we really need, we have to be able to see them on the screen. We have to be able to trace them. But they are built with actor and components, with all the interactivity you can have with them. But the price of that is that they live and die on a game thread. And that's why we create those on that thread. And we can try to figure out a process in which you're gonna merge your asset during the cook, but that's not gonna solve your issue with working inside the editor. And at the same time, it makes iteration on the game map a bit more difficult. And merge asset, they're not gonna utilize the repeatable geometry that you're gonna have. Like if you're gonna build the house or you're gonna build the village, you're gonna introduce a modules that you're gonna repeat again and again, making the memory footprint a bit lower. And to be honest, I'm not really keen on constantly creating new objects, because garbage collection is also something you have to be aware when walking through the world. And we use actor and component because it's convenient. The composition, the blueprint support, it's building block of every single plugin you can figure out on the marketplace, and they're pretty awesome. But at the same time, we increased the complexity of those in time. I post here the sizes of those classes, but don't focus on the size itself. Think about the complexity of those systems. Skeletal mesh is so huge, it provides you with so many functionalities. Reworking that, it's very difficult. Optimizing that, probably possible, but we have to remember how many tools we have that use those primitives. And I'm not sure if we can ensure that all of them gonna work after we're gonna finish optimizing. But going back to our static environment, when we really think about it, we can really give away the interactivity that you normally have with actor and component. As I said, we're not gonna move around those objects. We just have to see them and we have to trace them. So we posed ourselves a question, what we could do if we wouldn't have to rely on the actor and component. What if we could create those proxies without ever creating a U component? So we decided to build this simple demo. And basically, this is 10,000 static meshes that they are animated with scene function. And what we did, we introduced changes to the engine that allowed us to create the render proxy without creating actor and component. And I want to shortly describe what we saw when we initially built that prototype. This is profiling data from the vanilla implementation of that. I have the actor spawner that it moves up and down the meshes. And you immediately see this massive parallel 4 that happens there. It spans across multiple cores, and it tries to move the update to the render thread. It then queues the render thread update. And then you have the render thread. Almost everything on the render thread was single-threaded, and it was processing one by one all those updates. But when we ran our proof of concept, what you're gonna immediately see is that we removed everything from the gameplay, from the game thread. We had own thread that was doing exactly the same, and we didn't have any massive parallel 4 because we decided that we wanna batch those calls. And if you look closely on the render thread, you're gonna see that we actually broke the flow of the render thread, but we were okay with that because we understood what was happening there, and we understood that we have to fix that. But immediately, with our proof of concept, we realized that we went from 16 milliseconds on average to 40 milliseconds because we changed the approach, how we interact with all those systems. We actually removed all this parallel processing, the send of end of frame updates. And we did that by batching those updates, by releasing those in batches that render thread could seemingly process. We had some spawn improvement, but since we were working on the worker thread, that wasn't really important for us. It was enough that those primitives lived and died on different threads. But the render thread became our immediate main focus because it wasn't efficient enough. If you look closely, the parallel 4, we were constantly hammering the same lock. We are allocating memory again and again for small bits and pieces. But we didn't saw it as a big issue. We knew what was problematic, and we had some ideas what we can do about it. And at that point, we actually contacted our colleagues at Epic, and we discussed how we could improve that. And Jarosław Bronisz and Zach Bettel, they actually work on that very heavily. They implemented new queue. They tried to offload some of the work to pipe threads. And I'm really happy to tell that exactly the same scenario with Unreal 5.4, it's around 32 milliseconds long. You immediately see that the queue, it's in much better condition right now. The render thread isn't that starved because we start processing much sooner than it was happening before. And there are much more optimization there. There is a caching that is involved in the whole thing. But for details, please contact guys or read the Epic materials. But then we merged. And this slide is actually my meditation on the topic of merging. Because we introduced changes to the engine, and we wanted to build upon it. And we knew that we need a lot of time to bring all the features we wanted to implement with that. With long projects, if you're gonna work on something 5+ years, you're gonna have to sync new version of the engine. And for me and for a lot of us, that process was always very difficult. So we wanted to figure out the way how we could do all the things we wanted to do with the engine, things that are a bit different than what you would normally see within the Unreal. So again, we reached out to our friends at Epic, and we described what we wanted to build, what are our results at that point. And we asked if they could introduce some of the changes that we did to the engine. This process was a bit lengthy because we had to provide the data, we had to describe what we want to do, and what is the minimal product they have to provide us with, so we're gonna be able to achieve that. But again, I'm happy to report that Dominic actually implemented all that. He introduced additional structures to the engine, and I will try to briefly describe to you what they do and what you can do with them. The first group of structure is a proxy description. The proxy description basically allows you to provide the proxy with the data needed for initialization. And the thing is, Dominic did something pretty cool because he already implemented the function for you, initialize from. And if you look inside that, you're gonna see all the code you need to write to initialize that proxy. But the even cooler thing is, if you figure out how to serialize the proxy data, you can recreate it without ever changing the engine. The second group is a scene description. The scene description is a structure that will allow you to provide scene interface with all the data needed to properly put proxy inside the scene, like bounding box. And again, we have already implementation, and we can look how Epic implements that for the primitive component. And the last bit is primitive component interface. This is something that we actually didn't figure out for our proof of concept. And this is the interface that will allow you to implement your primitive and interact with editor and also with cooked builds. But for the cooked build, this isn't really necessary. You can get away without it. And again, we have implementation that is ready to use, and you can base your implementation on it. And I'm not sure if I nailed that down, but we have to see everything Epic does as reference implementation. We have to understand that Unreal Engine isn't built only for us. It's built for all the industries around it, from movie through the automotive to the game dev. We all have different requirements. We all have different projects we are working on. And Epic, when they introduce something, they have to ensure that it works for all the workflows inside the engine. But when we build it, we wanted to have just a portion of that. Like, for example, with our implementation, we totally ignore static lighting because we know we're not gonna use it. We're gonna rely on dynamic. So at that point, we knew that we have primitives that we can build. We knew that we don't have to merge, but what we really wanted to do with them. And the answer is we wanted to utilize the CPU better because there are cycles we are wasting. And before you start, you start moving things and reducing the scope of the game, maybe we should start looking at those cycles and utilizing it. But to do so, we have to define something that we call hybrid solution. So basically, this is our approach, how we're gonna move forward. We're gonna build our gameplay with actors and components, and we're gonna use all the interactivity, all the plugins you can have with them. But for elements that are not strictly gameplay related, like environment, we're gonna use our simplified structs because they will offer us a greater performance and flexibility in other areas. So we went turbo. We introduced something that we call TurboTech. And the TurboTech is a framework and collection of the systems that are gonna provide us with specific functionalities, starting with multi-threading. Multi-threading is always difficult if you have to iterate on your solutions. If you have gameplay programmers, they're gonna rework stuff again and again until they find the proper feeling for whatever they're trying to build. And I believe that if you put some restriction to what they can do, you can actually get away with quite simple systems that you can reason if they can run in parallel. For that reason, we created Job Resource Entity System. This is a framework that allows you to write very small jobs and execute those jobs on a background thread, because we wanted to have a bit of asynchronous behavior. We have the runtime dependency graph, but in the future, maybe we will have to optimize to the static. We built in some thread safety mechanism, so our users, they can have immediate feedback if what they do can run safely in an environment that constantly is changing. We wanted to have jobs, because with small jobs, you can actually reason about what is the input and output of the job and what is actually happening inside. And my favorite is that if you have a job, the structure of the job is so different that it's very, very easy to distinguish between original Epic code and code that is written for our system. Those jobs, they're gonna have dependencies on other jobs and something that we call resources. And resources for us, it's an abstract language that allows you to define data dependency. And we use that information to ensure that two jobs can run in parallel. We provide the user with runtime proof of thread safety, and basically it's a base for multi-threading we are trying to build. And the last part is entities. And there may be two important things about this system. The one is that we try to map one entity to the component. And the second, that we actually don't build that for the cache friendliness. Instead of that, we build the entity system to support our multi-threaded model. And it's kind of visible on this graph below, and I will try to explain to you. We decided to divide our entities into two logical resources. The first one is the entity reservation. And during that time, if you have that resource, you can actually create additional new entities. But at the same time, since a different resource is the entity that is attached, you can process it. You can process all the entities that are already attached to the scene. And the only point of synchronization is this attaching process. But again, it's a very lightweight process. It's just changing 2 bits in a bit set. This is a very crude example of the job where you're gonna use our JRE context to create a view to iterate over entities. And you're gonna create a view with TurboSyn component, with the components that is called TurboSyn component, but the entity would have no decals attached. And then you can just iterate over the view and change the properties of those entities. And to request the job, what you have to do, you just have to provide us with the rights you wanna have. And this is the second part of the slide. This resource access rights reserve. You're gonna reserve the read access to the entities because you wanna filter the list of entities so no one can attach anything at that time. And then you want to change, you wanna have mutable access to TurboSyn component. And that information alone allows us to run 2 jobs, and if they don't try to don't have conflicting access to those resources, we can just run them. Turbo structures are our components in ECS model. And as I said, we have the entity being representation of the single component. And again, I showcase the sizes of those structures, but think about complexity. We removed a lot of the code that we don't need, and we provided much simpler API for our users. It's more restrictive, but at the same time, it allows us to build something that we can scale. The turbo storage is our answer how you want to serialize the data. Because serializing the proxy data is the most important step with what we do. Because as I said, if you have that data, you don't have to have components anymore. And the thing that we realize that we can compress the data if we divide it into specific section. The first one is the description archetype. Like every single element in our scene has a flag if it's gonna cast shadow. And we don't have to repeat fields like that again and again. We just keep the archetype information, something that is repeatable in that structure, and our proxy gonna just read it from that single instance in the entire game. We have the instance data, and this is something unique like transforms and overrides. And then the last bit is a bit more interesting, is runtime instance data. Because some of the bits of the data you don't really want to serialize raw. Like for good example is dependency on new assets. You don't want to have hard references. You want to have soft pointer and then in runtime resolve the asset. For our entities, we have even simpler representation because essentially what we have, something that we call entity archetype, is just the information which type of entity it is, where is the data, and what is the recipe to create entity out of the data. It really allows us to compress the whole streaming information and allows us to deduplicate a lot of the data inside those packages. Turbo Entity Streamer. Right now, we know that there are entities and we know that there is a storage, but during the runtime, you actually want to load specific entity from the storage. You have to have information, you have to resolve a recipe for those entities. And this is exactly what Turbo Entity Streamer is doing. We use Turbo Interop ID. This is unique ID of every single entities in the world. And just with that information, we are able to find the proper packages and create the entity during the runtime. And essentially, it is just the collection of the jobs. And finally, turbo streaming. This is our solution for streaming. But before we even start talking about some of the details, I think I first need to answer why we implemented that. And the first obvious thing is that we wanted to have much more control over how the streaming is happening within the engine. We had custom structs and we knew that we can stream them on other threads. And we had the choice. We could either extend the word partition or write own solution. And extending the word partition would put us again in a situation where we had to merge and resolve conflict with every release. So it was to some degree much easier to build from scratch. But also we wanted to have concepts that word partition doesn't support. Interior, exterior streaming. We wanted to have proxy meshes and we wanted to have collision that could be streamed in without graphical representation. And maybe the most of all is that we wanted to run our streaming alongside the word partition because we're always going to have things that we cannot turbify. We're always going to have things that has to be built with actor and components because we need the interactivity part. But also, word partition was and still is the fallback system we can rely upon to check if what we stream is what our designers built. So the turbo streaming, it uses all the systems I mentioned before. Our turbo interop ID is just 64 bits. We cluster objects in the packages based on relative distance, and we allow you to stream in and stream out with single component granularity. Since everything happens on the worker threads, it's asynchronous. It's gonna load in time as asset came into the scene. For us, it's more important to have fluid frame rate rather to have and we accept having popping in the worst case scenario, rather than waiting for things to synchronously load in. And we do it by the process we call turbification. So what we do, we build the world with actor and component, we put those on the level, and during the cooking or in editor on demand, we run this process. And this process, it loads actors, it checks if we can represent specific actor with our representation, and if so, we just discharge the actor from word partition, and we take ownership to bring those elements to the scene as needed. In editor, it's invisible for the user. You just put level instance on the level and click buy, and it's gonna happen for you. If you look closely, in this specific example, we reduce 1,000 actors to just 150. Those are elements that we just don't support currently. And on the right GIF, you're gonna see editor mode in which user can adjust streaming distance for individual object in a scene. The whole process is non-destructive. So as I said, you can in any moment you can run word partition and compare your result to be sure that our streaming does exactly what you want. So I put this small demo, and what you see is the small village in the center of the screen. It has around 4,000 of actors, and I repeated it a couple of times on the map just to have a bit bigger load. We use here all the elements we have of that technology. We have interiors, exterior setups, we have proxy meshes. The camera is running on the rail just to have repeatable scenario that I could compare. And this is the console performance data, and this is the part of the system we are using. So basically, we have here two runs, one with the vanilla word partition, and this is the blue data, and the red data is our word partition with turbo. And what you're gonna immediately see is that on the first graph, we have the game thread time, and we eliminated all those spikes, those big spikes that you're gonna see. They were related to adding to word new elements. But if you look closely, we have still some of the red spikes, and those red spikes, they are associated with process async loading. Because as I said, if you wanna have very granular streaming, you have to constantly stream in and stream out assets. That's why we're gonna get back to that topic, and definitely we'll have to figure out how to move some of those functionalities away from the game thread. And lastly, the last element on this picture is number of primitives in a scene. Because we have interior, exterior streaming done separately, since we have proxy meshes that allow us to have a better control over how we load elements in a scene, we have much fewer primitives. Instead of having around 18,000 as with original implementation of word partition, we have just over 8,000. But actually, we did a bit more than what you're gonna find within the Unreal. We worked on decals, we work on points, and we work on my favorite skeletal meshes. Skeletal mesh is one of the heaviest components to have in a scene. And to be honest, with all the titles I worked previously, that was something that was limiting our vision, what we can achieve with that. But here on the screen, you actually see 1,600 skeletal meshes, each animated with own animation. And if you looked at the profiling data between the left vanilla and right our turbo implementation, you're gonna immediately see that the game thread is basically just sticking those skeletal meshes. And on the right side, you're gonna see the 4 threads that they are processing our jobs. They do it in parallel. They send all the updates to the render thread. We don't have to rely on those massive end of the frame updates anymore. And on the game thread, we just stall because we realize that if we don't wait with rendering scene until we finished updating the primitives in a scene, we're gonna break it. So if you put any logic on a game thread, you're gonna get that time back. We have more changes that were needed to achieve that. Like for the physics, almost everything already is decoupled. What we needed to change is some of the function, they have like static inside, and because of that, static members. And because of that, you couldn't create bodies in parallel. And we actually reworked a bit task graph scheduler because we wanted the task graph scheduler to be aware that we're gonna run additional system based on it. And we have very small word partition extension, which allows us to discharge the turbified actor from the scene. But to be honest, the change was so small that we decided not to push it to the engine because you can replicate it quite easily. If there are any takeaways from my presentation, I think the most important is that Epic cannot solve all our issues. We have to do it ourselves. But what we actually need is some small engine modification that will allow us to do so. It's much easier to work with someone when you come in with the data, when you come in with the ideas, how we can improve, and you are ready to iterate on those things. We always look at what Epic does, we analyze all the changes within the engine, and we think how we can leverage what they already built. If you have your own project, if you have the pipelines that you decide to support, you can really gain a lot of performance back because you can simplify the processing paths. But you have to be very careful with what feature sets you're gonna use. The only thing that we cannot do, we cannot end up with merging hell. We cannot end up in a situation where updates of the engine gonna be something we're gonna avoid. You wanna be as close to the main development as you can. The good example is this 5.4 release. It's amazing. It gives you a boost in performance for free. You just have to integrate it to your code base. But most of all, what we have to all do, we have to be very vocal how we change the engine, because those patterns, we intend to discover them again and again through different companies, and we don't really know about those until it's very late. Maybe we speak about those after we release the game, or maybe we never speak about it because we already solved our issues. And that will be all. Thank you.